Hey, seniors. Glad you could join me here. We're going to talk about some groundwater stuff, right? So we've been thinking about groundwater a lot with these questions of contamination related to the ghost map, the articles you read last week. So we're going to dive more deeply into the basics, actually. We're going to back away and dive more deeply into a different aspect of this, which is just understanding the fundamentals here. And then we normally look at the case study of Woburn, Massachusetts, and we'll mention it here. But that's a situation where you had several companies that were dumping trichloroethylene and a couple other chemicals onto the ground and into streams locally in Woburn, Massachusetts. Pretty classic. You can watch the movie A Civil Action with John Travolta. Great movie. We normally watch in class, but can't do that this year. So basically, if you remember any of your earth science, the water table is what we think about most of the time when we think about groundwater. But it's important to think about groundwater as the water that's contained within the ground, of course, but it's not sitting down there in lakes and rivers. It can be actually if it's sitting in a cave. That's a little different. Most of the time, though, we're talking about water that's saturated within the pore spaces inside of a rock. Yes, inside a rock. You can put water through a rock because rocks are made of sediment particles. Those sediment particles are glued together, but there's pore space inside of a rock, and that's where the water's moving and sitting most of the time. And so the pore space, the permeability, how well those pores are connected, and are all are major important factors. And then this week we're going to be focusing on those questions of pore space, porosity, Darcy's law, and so forth. So, but the water table is, of course, the top of the area of saturation, the zone of saturation, and the area above that is mostly water. There is a capillary fringe right above the water table where water will make its way up through capillary action. But generally, this is how we break things up back in earth science, and that's almost the extent of it. The other thing to note is that groundwater doesn't just sit there; it moves. It's under the force of gravity. It also mimics the topography, and so you see this water table here has this sort of wavy look to it, as the land above it does. And this affects what we call hydraulic head and the ability of groundwater to move around. And that's important. Groundwater is also connected to streams. Some streams are gaining water from the groundwater. Some are losing their water to the groundwater system. So there's a connection here. Groundwater is not disconnected from surface water any more than surface water is disconnected from the oceans. All these things are connected. So typically, they have these sort of ideal situations where we have these sand and gravel aquifers up in the northern tier of the country. Up here, we have a lot of those because they're left over from the glacial periods, of course, in the Pleistocene when the glaciers deposited those. A lot of the other aquifers, the further south, are the result of being in bedrock or fractured bedrock, typically like around us. Okay, so in a typical sand and gravel aquifer, you have the water table here. This is an unconfined aquifer. So the water table is open to the zone of aeration, and there's no aquiclude or clay layer sitting on top of it to prevent it from moving, being pulled upward to a well or whatever. We'll typically sink a well into the zone of saturation to try to get water out, right? And if it's a sand and gravel aquifer, it behaves differently than if you're sinking a well into a fractured bedrock aquifer. It behaves very differently, of course. And here we got the example of how the water table is interacting with a local stream and so forth. So this is a great little diagram. So sometimes you have porosity, again, is the empty space within the aquifer that the water sits in. And the porosity can vary. So like if you have sediments of a single grain size, and you're going to learn about this week, you'll have more porosity than if you have sediments of a mix of grain sizes. The porosity will generally be less because you have bigger sediments, but then you have little sediments filling in those what the bigger pore spaces are. So this is pretty typical stuff. But if these pore spaces are connected, then we call it permeable. And typically, permeability varies based on the type of aquifer. So we're going to be looking a lot at sand and gravel, but typically in a fractured bedrock situation, permeability can be, the water can travel anywhere from 1/10 of a foot to 3 feet per day. 3 feet per day is actually pretty fast for an aquifer. In sand and gravel, it can actually travel much faster. If you're looking at clay, the aquiclude type stuff, the layer that would prevent water from moving, We said if it's moving at like 1 foot per 10,000 years or 0.1 feet per year, that's very, very, very slow. So it's essentially impeding flow is what it's doing. And of course, then we get to the term hydraulic conductivity, which is directly related to permeability and porosity. And it's a term we use to describe, sometimes represented as K in Darcy's law. It's a term we use to describe, you see it's in feet per day, which is the velocity, the rate of movement in an aquifer. And of course, that's related to gravity and so forth. But different kinds of aquifers have different hydraulic conductivities, and I'll show you another. I'll give you another handout with this as well. Fractured bedrock aquifers are very similar, except that the materials are mostly moving through fractures. They're still moving through the rock, still, but the fractures are really, really critical because that's where the really high hydraulic conductivities are. Because obviously the water's less impeded. It's basically moving through a giant pore space, is what it's doing in a fracture. And fractures tend to be connected. And fractures tend to be determined by the structure of the rock, how the moon has pulled on the rock over time and broken it and fractured it, how mountain building events in the past have created fractures and so forth. A lot of important stress and strain questions being that lead to the way fractures are patterned in rock. So we get into Darcy's law. Darcy was a French hydrologist who came up with this very simple relationship between gravity and the material in an aquifer and the amount of water or volume in terms of volume over time, discharge, that an aquifer could produce. And we assume in Darcy's law some basic assumptions. For it to work, we have to have the material has to be homogeneous. It has to be consistent throughout. We assume it's isotropic. It's the same throughout. We assume that the aquifer is laterally infinite, which obviously none of these things are true for aquifers generally. We also assume that it's a sand and gravel aquifer and that it's an unconfined aquifer. Darcy's law presents us with a model. Models are always wrong, but sometimes they're useful. And this is one of those useful ones, so that's why we talk about it. Darcy figured these things out by using creating an experiment with a tube, but we're going to do the same thing in class, something very similar, in a very similar manner, where he was able to measure as if you put water through inlet here and measure the discharge at inlet here, you can measure the discharge going in and measure the discharge going out, and then you can measure the speed at which the water basically moves through here. That's the hydraulic conductivity. That you might have this filled with sand or gravel or whatever. So the water, of course, if you had piezometers, that's what they're called, sticking into the Darcy's apparatus here, you can measure the hydraulic head at one location, at another location, and take the difference there over the length of the tube. That's your gradient. It's dimensionless. And multiply by the cross-sectional area and then the velocity, you can get you figure out what the discharge is here. And that's what's going on with these various forms of Darcy's law. This is the form that we'll primarily focus on using. We can rearrange it a little bit to solve for hydraulic conductivity if we know what the discharge is. And that's what we're going to be figuring out next week. So this is really basic stuff, right? This is how we can measure and model and predict how fast and where water molecules are moving. And where water molecules are moving, contaminants are moving. Now you think about the ghost map. If we can model the aquifer in around that the Broad Street pump is pulling water out of, then we have some idea of how fast the cholera can make its way from cesspits into that. There's more to it because you're pumping water out. There's another set of equations for that. We still have some idea of how the aquifer behaves. Now, in a confined situation where you have a clay layer that is above the aquifer, we call that a confined aquifer. You can still drill a well in there. We call that an artesian well. An artesian well is a well where the water will rise up under its own pressure, essentially, to what's called the potentiometric surface, which would be the water table without the confining layer, is what you might think about it. In an unconfined aquifer, the water table itself is generally the potentiometric surface. It's the level, potential level that the water would rise to in an unconfined situation. That's how I tend to think of it, even though it should be described technically differently. If the artesian well or the potentiometric surface is above the ground, then the well will run and flow on its own without being pumped. So anyway, if we move on here, You can have examples of this where the potentiometric surface can be modeled. We can actually use contours, much like we do with the land surface, to model a potentiometric surface. And if we have wells and we know where the water levels are, we can create a contour map. And we create a contour map, we can then say something about how the water is moving, because flow lines will move perpendicular to the direction, and they're going to move downhill. Water is going to move downhill all the time towards the lowest spot. And so we can predict where the water is going to move if we know what the potentiometric surface looks like in an area. We can model this. Again, we have to have a bunch of wells for that, but it does work. Excuse me, this is an example of that from Georgia. So we have all these little black dots or wells. We know what the depths of the water are, and we can take that, and we know what the water depths are, and the land elevation depth, we can actually figure out what the water depth is. So an example in a humid environment, in a stream that's gaining water from the groundwater, gaining stream situation, the potentiometric surface lines will look like this, which is typical for topographic maps, the rule of V's, right? But it can be the opposite when you have a losing stream situation like this. All right, where the potentiometric surface lines behave differently. All right, so let's talk about mapping contaminant plumes a little bit. There's a lot of different kinds of contaminants. You know, what's in that bath water? What makes it dangerous, right? And that's kind of the one of the big cruxes that we're thinking about in environmental geology is how we understand the basics of an aquifer and how it moves and how we pump things. But then what about these organic contaminants? Many of these are inorganic ones, like mercury, lead has been in the news, of course, the last few years quite a bit with Flint, Michigan. And then there's organics, pesticides, fertilizers, gasoline, things like that. And then microbial, you know, bacteria, E. coli, cholera, so forth. Some of these are what we call NAPLs, and others are DNAPLs, LNAPLs and DNAPLs. Okay, they're aqueous phase liquids. So a dense non-aqueous phase liquid are things like heavy oils, things that are denser than water. They're going to move to the bottom of an aquifer, and then you have to try to clean them out from there. They can be pretty thick. They can also tend to sorp onto organic matter in an aquifer and be stuck there. You can never fully clean an aquifer out. It's impossible. You can just make it better, which is why you shouldn't pollute it to begin with, but there's not a lot of regulation on that. So light non-aqueous phase liquids are things like gasoline that sit on top of the aquifer, and when those plumes spread out, they tend to spread out on top of the aquifer instead. So some of these are miscible, some of these are less miscible than others in terms of like how they mix with the water. So here's a simplified subsurface LNAPL process. If we dump our release source, our gasoline perhaps, there is vapor that comes out of that, of course, and then the LNAPL itself will spread out mostly along the top of the aquifer, and some of it may dissolve depending on what's in the LNAPL, and then it'll move along with the groundwater. So we can model, if we know where the groundwater is moving, again, we can model a potentiometric surface, we can predict, and then the hydraulic conductivity, we can predict where and how fast these things are going to move. There are other processes involved. Advection and diffusion are important processes with this. This is how materials get pulled along. If they're not mixing specifically, they can get pulled along through the aquifer, through both the groundwater zone and, of course, the vadose zone, or the zone of aeration, is primarily a downward movement. And then when the groundwater gets in the groundwater, it's going to be moving laterally as well with the groundwater. All right, so here's another example of advective flow. That's being pulled along with the groundwater movement. That's advective flow. You have a DNAPL here as well, move to the bottom of the aquifer, and it's going to move along also, but the bottom of the aquifer doesn't tend to move as fast. And so DNAPLs don't tend to spread as quickly as LNAPLs do. And so we can model this. One of the big problems that you don't think about, even if you're not pulling water out of that aquifer that's contaminated, you still have, especially things like VOCs, volatile organic compounds. You have materials that are releasing fumes, and they come back up through the aquifer, through the vadose or aeration zone, and they can move into your basements and cause lots of health problems that way. Plumes can be modeled using software, and this is an example using a piece of software called Rockworks.
Plume modeling is to enter the data and generate strip logs. In this example, relative benzene concentrations are shown by proportionally scaled and colored dist. The next step is to use the Rockworks modeling capabilities to generate a block model based on these benzene values. By filtering the model values based on a user-defined threshold, we can see the shape of the plume as well as the volume. By combining stratigraphic or lithologic fence diagrams with plume model.
So that's pretty cool, right? You can, if you just have information from a bunch of wells, you can begin to actually put together and extrapolate what the plume actually looks like. Pretty important stuff. Now, this is all about Woburn. We're not going to get into this because we're not going to be using Woburn as a case study at this point. But I was spending time talking about some of these glacial deposits that are up there. We're going to leave it at that for this presentation. So I hope you enjoyed it. I hope you got something out of it. Eventually, we're going to talk about some of the equation, the Tice equation. Not this week. We'll do another one of these on that. That's how you model the drawdown in a pumping well. And that's the other part of this. If you're going to pump this stuff back out, like they do at Broad Street, or like you do at home with your pump, then we got to think about how contaminants in water are going to move in that situation. That involves some calculus. So we'll come back to that. All right. Have a good day, guys.